All right, folks, we are going to get into the Lewis dot structure portion of Unit 6. This is certainly going to be the meat and potatoes of the Unit 6, okay, of the bonding unit. It's going to be extremely important for us to understand the ability that we have to draw Lewis dot structures. Let's see here. So what we want to do right now is understand what a valence electron is. Okay, valence electrons are going to be your outermost electrons. Those are going to be the electrons found in the s and the p sublevel. So let's take a look at our periodic table real quick. Okay, remember back to the electron configurations that we were doing, where we had 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Okay, so I remember that when I get into this D section, or into a period 4, it was 4s2, then it dropped down to 3, and then it went back up to 4. Okay, so that means that anything in this D section is not going to be included when I'm referring to my valence electrons, okay? Because now I'm talking about energy level 4 for 4s2, energy level 3 for 3d10, and energy level 4 for 4p6. So that's why my s and my p electrons are going to be my valence electrons. So this says that valence electrons are helpful for predicting what's called the oxidation number, and that's our predicted charge, essentially. Okay, so how do I know what elements are going to be what when it comes to their oxidation number? Well, I can use the last digit of the group number to help me think of what my charge is going, or what, how many valence electrons I'm going to have. So group number 1 is going to have 1 valence electron. Group number 2 is going to have 2 valence electrons. Group number 13 is going to have 3. Group 14 is going to have 4. Group 15 is going to have 5, so on and so forth. Okay. Now, this 1 valence electron and when I go back to my periodic table, I remember that group 1 is all metals. I know that metals are losers, so it's going to lose that 1 electron that it had, thus making it a +1 charge. Okay, all of these, they're all metals, they're all losers. So all my group 2 metals are going to lose both of their valence electrons to form a +2 charge. Okay, everything in group 13, okay, I've got metals, and metals are losers, and so this is going to give us a +3 charge. Now when I get to group 14 and 15, we're going to start doing some weird things. So let's jump all the way over to 16 and 17 real quick, so that we can focus on them. Group 16 is going to have 6 valence electrons. Almost everything in group 16 is a non-metal, okay? And we know that non-metals are going to gain electrons. So oxygen's going to gain 2 electrons to act like neon, giving it a -2 charge. Sulfur's the same thing. It's going to gain 2 electrons so it can act like argon. Okay, remember isoelectronic? That's the term that we would use for it gaining electrons to act like its nearest noble gas. Fluorine, chlorine, bromine, iodine, so on and so forth. Anything in group 17 is going to gain 1 electron because they already have 7. Since they already have 7 electrons, they're going to gain 1 so that they can now have 8 electrons so that they can behave like the noble gases. Okay, so all of these would form a -1 charge when they are in their ionic form. Now let's go back to group 14 and 15 for a moment. Group 14 and 15, those are the weird ones. Okay, we have non-metals and metals in group 14 and 15. Okay, so here's what we've got. Group 14, carbon and silicon are non-metals. Non-metals are gainers, so these are going to actually gain 4 electrons to act like their nearest noble gas, giving them a -4 charge. Okay, oxygen, sulfur, and selenium in group 15 are going to gain 3 electrons to give them a nitrogen, phosphorus, and arsenic are going to gain 3 electrons to act like their nearest noble gas to give them a -3 charge. So carbon and silicon, -4. Nitrogen, phosphorus, arsenic, -3. Okay, now let's look at what's below the stair-step line, okay, or on the left-hand side of the stair-step line for group 14 and 15, okay? Group 14, let's focus on that. Germanium, tin, and lead. We're going to knock your socks off real quick. This is going to get crazy because of the things that these can do. Now, these can lose just their p electrons, or they can lose their p and their s electrons. Okay, let's take tin for example. If tin loses just these 2 p electrons, it's going to form a +2 charge. If 10 loses the 2 p electrons and these 2 s electrons, then it's going to form a +4 charge. Okay, same for germanium, same for lead. Okay, those can form a +2 or a +4. If it only loses its p electrons, it forms a +2. If it loses its p and its s electrons, it forms a +4 charge. Okay, so all of these little fellas right here can do that. Now, let's look at antimony and bismuth. This one's really going to get crazy. Antimony and bismuth can do the same thing. They can lose just their p electrons to form a +3 charge, or they can lose their p electrons and their s electrons to form a +5 charge. So our metals, our p block metals can get pretty crazy. Okay, so just remember that. That's going to be one of those things that you're going to have to kind of practice with to get a good grasp on. Okay, it says also the oxidation number for pure elements, meaning that an element that's just by itself. Okay, if it's by itself and it doesn't, it's not an ion or anything like that, then its oxidation number is going to be 0. Okay, that's important to understand. So just a regular old atom is going to have an oxidation number of 0. Okay, so why have we not discussed? Okay, so yeah, why don't we discuss charges for our noble gases? Okay, the reason for that, of course, is that there's not an oxidate. They don't have a charge. Okay, so since they already have all the electrons they want, they're not going to do any sort of reaction or anything like that to form a charge. Okay, so now let's take a look at our transition metals. For our transition metals, the oxidation numbers are going to get a little interesting. Okay, these don't really behave. Okay, transition metals can have multiple oxidation numbers, and we don't necessarily know what what their charge is necessarily going to be. However, there are 3 that we do know what their charge is going to be. Okay, silver is always going to have an oxidation number of +1 every time, every time, every time. Silver has an oxidation number of +1. Zinc and cadmium always have an oxidation number of +2, and it works out because silver's in group 11, and if you want to, group 11 +1, these 2 are in group 12, +2. You know, that's a way that you can kind of remember it with the last digit thing. But don't let that be the only way that you remember it. Okay, silver can be +1, zinc and cadmium are +2 always. Okay, all of the other transition metals, however, all of these other transition metals can have multiple oxidation numbers, and so we have to be told what their oxidation number is. So that is what I was talking about right here. So this next little bit wants you to use this periodic table to determine some common oxidation numbers for some different elements that we have in the periodic table. So we know that all the group 1 elements minus hydrogen is going to be +1. Okay, all of our group 2 elements would be +2. All of our group 13 elements +3. Group 17 -1. Group 16 -2. Group 15 -3, except for these weird ones down here, which are on the left-hand side of the stair-step line. This one can be +3 and +5. Okay. Also, don't forget about these. There's zinc, cadmium, and silver. Okay, silver is going to be +1, and zinc and cadmium are going to be +2. Okay, so you can kind of fill in the rest of this the way you need to, but that's going to give you an idea of those common oxidation numbers for the periodic table. Okay, that gets us to Lewis dot structures, but holy smokes, it took me 9 minutes just to get there. So we're going to take a look at Lewis dot structures on the next video. So yeah, great stuff.